and she claims that static equipotential photon surfaces have no hair. Please, Carla.
Thanks very much, and thanks for the invitation and for all the interesting talks I've been able to hear so far. We'll switch gears now to a more theoretical perspective and actually not consider stationary but only static spacetimes in this talk. I may be able to say a few words of outlook towards the stationary case towards the end if you're interested. So I would like to recall that, of course, everybody knows the Schwarzschild-Tangellini spacetime, and I'm mostly writing this down to introduce notation. So the Schwarzschild or Schwarzschild-Tangellini spacetimes in 1 plus n spacetime dimensions looks like this, or it's metric rather, and d omega squared is my notation for the canonical metric on the sphere. And it's well known, of course, and we've heard it already alluded to today, that if the mass is positive, then there's a photon sphere cylinder at a certain radius in 3 spatial dimensions. You're familiar with this photon sphere sitting at r equals 3m. In higher dimensions, this is the formula that, this is the formula that produces the very same phenomenon, okay, for positive mass, and n is the spatial dimension here. In 2003, Furch, Hasse, and Volker-Perlich have considered this spacetime in the case of n equals 2, so where the sphere is just a circle. And they have constructed a plethora of spherically symmetric so-called photon surfaces. So here by a photon surface, I mean an umbilic time-like surface. So just like the photon sphere would be one of the examples. Now here we have 2 spatial dimensions in 1 time direction. But they found a lot more than just the cylindrical ones. And the definition, the mathematical definition of a photon surface here can be worded either as an umbilic time-like surface, where umbilic means that the extrinsic curvature is proportional to the induced metric along this hypersurface. And if this is not so intuitive to you, a logically equivalent formulation is saying it's a time-like surface along which any null geodesic that's ever tangent to it stays tangent to it as long as it exists. Okay, this is true for the photon sphere, but they found for n equals 2 in this Schwarzschild-Tangellini generalization to 2 spatial dimensions, they found a whole zoo of such spherically symmetric photon surfaces. And I have a picture here that I'll enlarge for you that we drew, we reproduced from their work. So the red line R star is the photon sphere in an RT diagram here, R being the radial coordinate in the Schwarzschild of whatever dimension we're looking at, and T being the time coordinate, and the angles are suppressed here. So we're just drawing the radial profiles. And so they find curves, radial profiles of rotationally symmetric photon surfaces of the kind that comes in from that comes in from tangentially to the photon sphere and goes out to infinity, or another type that they find photon surfaces, that emerge from somehow tangentially to the horizon, then bump around and go back tangentially to the horizon, and another kind that looks like this. It looks like more or less like the radial profile looks more or less like a hyperbola, coming in from infinity and moving back out to infinity. So these are the radial profiles, let me stress this again, of the rotationally symmetric photon surfaces identified in 2 spatial dimensions Schwarzschild by Furch, Hasse, and Perlich. And others can come in, from the black hole horizon and then move away to infinity. And all of these also exist in their time reflected versions, and they also all exist in their time translated versions. And this is due to the time translation and time reflection invariance of the Schwarzschild spacetime. I forgot to mention one type. There's this one type which I should have probably drawn here. So we have this one type that comes from the horizon and asymptotes the photon sphere, and this other type that I drew in the wrong picture, which comes from the horizon, turns around and goes back tangentially to the horizon in this way of depicting it. Okay, so these are the different types of photon surfaces that they find. And what I've looked at together with Greg Galloway in a work that's recently been published is that it is the higher dimensional case, so the case where we have at least 3 spatial dimensions. And here is a list of the results that we find. So first of all, we find the exact same plethora, the exact same zoo of rotationally symmetric photon surfaces I just explained to you in these higher spatial dimensions, in particular in the 4-dimensional space-time case, where again here a photon surface is defined as an umbilic time-like now hypersurface. And more generally, we find the exact same phenomenology in spacetimes of this form here, where you know that this of course includes Schwarzschild, but it also includes anti-de Sitter, it also includes Reisner-Nordström and many other examples, and we call those spacetimes of class S. And we find that the spacetime of this form has a photon sphere at a given radius r star, if and only if the function f at this r star satisfies this condition. And also it has a rotationally symmetric photon sphere, so photon surface, sorry, with radial profile r, if and only if this radial profile satisfies this ODE, where lambda is some positive parameter related to the umbilicity factor. It's exactly the umbilicity factor for those who know what this means. So the picture in a generic space-time of this class S looks exactly the same, so I'm not going to discuss it again, in case there is exactly one solution of this photon sphere ODE here, and I'll say more about this. So we find the exact picture in particular in higher dimensional Schwarzschild-Tangerlini starting in 4 space-time dimensions. Okay. So what else do we understand in this class S? We understand, on top of what I just said, that there aren't only rotationally symmetric photon surfaces, but there are also others which look like partial hyperplanes. Think of the Schwarzschild spacetime in an RT diagram now with angles. And if I cut a plane that contains the t-axis, of course it doesn't have an interior because of the black hole, but if I cut a plane in here containing the t-axis and keep the piece, the partial hyperplane, sitting outside the black hole, then this is also a photon surface by symmetry. But in all, and this happens in all these spacetimes in class S, and we can show that every photon surface is either rotationally symmetric or such a partial hyperplane, provided that the spacetime is nowhere conformal to Minkowski. Being conformal to Minkowski, meaning having the same angles as in Minkowski, is problematic, because in Minkowski, you have the photon surfaces, which are all time-like planes and all time-like one-sheeted hyperboloids, and they can be translated, and we cannot account for this translation in this conformal picture. That's why we have to make this orange restriction. Furthermore, we can show that if you're in a static spacetime of this form minus n squared dt squared plus g, where g is some spatial metric independent of the time, and n is my name for the lapse function here, and we are in spatial dimensions 1 plus n greater or equal to 1 plus 3, and we vacuum and asymptotically Schwarzschild, I forgot to say that. Yeah. Then we have the following theorem. If the inner boundary of this static vacuum spacetime, which is asymptotic to Schwarzschild or Schwarzschild-Tangerlini in high dimensions, if it has an inner boundary, and the boundary consists of multiple components, each of which is either a black hole horizon or photon surface, or for example, as a special case, a photon sphere, under this condition that the photon surface's boundary components are equipotential, I'll say in a moment what this means, then the spacetime is actually Schwarzschild-Tangerlini. So this is what I understand would be called a no-hair theorem in the physics community. So let me rephrase it as a no-hair theorem before I explain what this condition of equipotential is. So a no-hair theorem, it is a no-hair theorem in the following sense. If I have a static configuration of black holes, 0 black holes, 1 or more, and photon spheres and photon surfaces. And here I'm not visualizing them inside each other because all of them are boundary components. So they all sit next to each other. So I have a black hole here, maybe a photon sphere here, and another equipotential photon surface here. Then there's at most one of them, either a black hole or photon sphere or one of these equipotential photon surfaces. And the exterior region to it is exactly Schwarzschild or Schwarzschild-Tangerlini in higher dimensions. So I have no freedom, they have no hair whatsoever. So I still owe you an explanation of the term equipotential, which is an important assumption in this theorem that we cannot get rid of, it seems, at the moment at least, partially because of the existence of these partial hyperplanes, even in the Schwarzschild-Tangerlini spacetime, which are photon surfaces. So here's the definition of equipotential. If I have a photon surface, like in this picture, the green surface, it's a time-like umbilic hypersurface, and I intersect it in the static spacetime with a t equals constant slice. So any of the slices orthogonal to the Killing vector field, then I want the Lapse function to be constant on this cross-section. In other words, the Lapse function along the photon surface can only depend on its time component, not its spatial component. So in some sense, if you want, you can write this as n, the Lapse function being a function of t along the photon surface. Right? And this is, of course, given if I'm in a photon sphere case where I'm really a cylinder, where n is the Lapse function is actually constant along the photon surface, and is of course given in any spacetime of class S, so any spherically symmetric static spacetime for spherically symmetric photon surfaces, because then I have this condition satisfied a priori. So in my Schwarzschild-Tangerlini examples, it's satisfied exactly by the rotationally symmetric photon surfaces that I want to find in this case as inner boundary components. Okay? And I'm ruling out in Schwarzschild-Tangerlini these partial hyperplanes, which are also not boundary components, but in that case, but I'm ruling out this phenomenon. Another thing we can show, which maybe is more close to things that people here in this virtual room consider, is that rotationally symmetric photon surfaces in spacetimes of class S are actually the same thing as time-like hypersurface generated by null geodesics via rotation. So if I have any null geodesic with vanishing angular momentum, and I rotate it in space and around all the sphere of the spherical symmetry, then it creates a time-like hypersurface. And this time-like hypersurface will be a rotationally symmetric photon surface, and every rotationally symmetric photon surface will be generated this way. And the parameter lambda, the positive umbilicity parameter that appeared in the photon surface ODE, can be related to the energy and the angular momentum of the generating null geodesic in this way. So it's actually nothing else but E over L. So it's not a funny geometric parameter only, it's also very closely related to the conserved charges along the null geodesic, generating this photon surface, this rotationally symmetric one. And this insight allows us to show that the null section of the phase space of a spacetime of class S is actually partitioned by rotationally symmetric photon surfaces and rotationally symmetric principal null hypersurfaces. Those are those null hypersurfaces generated by rotation by null geodesics with angular momentum 0. So every null geodesic either has angular momentum 0 and then by rotation generates a principal null hypersurface, or has non-zero angular momentum, and then by rotation generates a rotationally symmetric photon surface. Okay, so having these insights at the back of our mind, there's work in progress I'm about to write up with my PhD student Markus Wolf, where we generalized all the above discussion and analysis to the case where here in the last part of my metric, instead of just looking at the sphere with its canonical metric, we can look at an arbitrary n-1 dimensional Riemannian manifold, maybe more of mathematical interest. But we can also construct Kruskal-Sekaras extensions, as those you know for the Schwarzschild spacetime, in all these metrics in class H, which encompasses the class S we've looked at before, if they have across any non-degenerate killing horizons they may have. And this allows us to actually consider what happens to these rotationally symmetric photon surfaces that we discussed previously if I look at those that approach the horizon. Yeah, here, so on the right-hand side here, I've drawn a little reminder of the picture that looked much more professional that we looked at in the beginning. And it turns out that the purple and green rotational profiles drawn on the right-hand side here in the TR diagram that appear to actually asymptote to the horizon actually penetrate the black hole and only look as if they asymptote to the horizon because we look at them in TR coordinates and not in Kruskal-Sekaras coordinates. As soon as we do so, we see that they penetrate the horizon. And those like the blue ones who look like they asymptote to the rotational hyperboloids in Minkowski spacetime in the TR diagram actually can be shown to do so when we use in a very strong sense in Kruskal-Sekaras coordinates. And this doesn't only apply to Schwarzschild, but in particular, it does apply to Schwarzschild and Schwarzschild-Tangellini, starting in spatial dimension 3. But the same should be true for lower spatial dimensions as well. And just to complement this with work in progress with my former student, Sophia Jans, and my current student, Olivia Vicanic-Martinez, what we've looked at is, again, this photon surface ODE that I've shown you before, where the parameter lambda was the embellicity parameter, or in other words, the energy divided by the angular momentum for the generating null geodesic of the rotationally symmetric photon surface. And in order to study how this ODE behaves in a more generic profile F was the function in the metric minus f of r dt squared. Yeah. So this profile, we've by analogy to this null geodesic analysis, we introduce this effective potential f of r divided by r squared. And then for Schwarzschild, of course, this effective potential looks as in this diagram here. And the different values of lambda actually correspond nicely to different energy levels in this effective potential diagram, which allows us to give a rigorous analysis and ensure that the picture we've seen earlier with all these nice profile curves actually is complete, and we haven't overlooked anything. And all these radial profiles are smooth, and this holds for any space-time with radial profile taking roughly this form. So it has a non-degenerate killing horizon here. That doesn't work. Then here, and decays, the effective potential decays to 0 near infinity. But we can also generalize this analysis to other situations where the asymptotics is different, for example, or where we have multiple turning points. Here, this turning point corresponds to the photon sphere of this maximum. Yeah? So we can do this analysis in a wide variety of spacetimes of class S, also in this more general class H that I mentioned before. And this class includes Schwarzschild, Tangellini, Reisner, Nordström in spatial dimensions larger or equal to 3, ADS Schwarzschild, ADS Reisner-Nordström, and also Kotler spacetimes with different spatial cross sections. And we can also generalize the no-hair theorem to asymptotically flat unique electrovacuum in this paper. Thanks very much.
Okay, thank you very much for the talk. And yeah, maybe we can allow ourselves one question. Is there a question? Don't see any, but I have one. Do you see a chance to generalize your no-hair theorem to the rotating case beyond spherical symmetry?
Not at the moment. We don't see a clear statement that we could hope to be true in the non-static case, actually, because we wouldn't expect the trapped photons to live on a hypersurface in the space-time, right? Even in Kerr, they don't do that. There's this expanded photon region, and you have to live to the phase space in order to get a nice smooth submanifold even. Yeah. So I don't see how this could be approached in the manifold itself, and we're still dreaming that we can approach it in the phase space. But then it's not a hypersurface, but a 5-dimensional and an 8-dimensional, and then it's not really clear what type of techniques one can use. Yeah. But we do hope that we can get some like quasi-local information near trapped photons, or maybe at least for small angular parameters, say in the Kerr family, understand what happens to the non-photon sphere photon surfaces, if anything persists.
Yeah, I have exactly the same impression, yes. Okay, thank you very much again for your talk. I think we